Hello, higher chemistry pupils, and welcome to this video looking at molar volume. This is a new concept for us as we're looking at gases, and this is just the first lesson in a series of lessons looking at how we quantify gases. So the success criteria, these relate to the 3B booklet, page 2. So I can explain what is meant by the molar volume of a gas and how it can be determined. So that includes what units molar volume is measured in and what calculations we can do to arrive at molar volume. And I know that molar volume is dependent on temperature and pressure. Okay, so let's look at a little bit of prior knowledge then before we get started on our notes. So we need to know what a mole is. Okay, so a mole is a chemical unit. It's a word that describes how much of something we've got, like a dozen would describe 12. And a mole of a substance is the formula mass expressed in grams. So 1 mole of methane, so methane has the formula CH4, and each carbon atom has a relative atomic mass of 12, and each hydrogen atom has a relative atomic mass of 1. So in total, that is 16. So the gram formula mass is 16. So 1 mole of methane weighs 16 grams. Okay, so that's the first thing we need to be happy with. And we also need to be able to use that mole in the relationship of masses and moles and formula mass. So that is that the number of moles is the mass divided by the gram formula mass. That's how we calculate that. And you might see that in these kind of triangle relationships like this. Okay. The second thing is just some concepts of solids, liquids, and gases. So this relates to learning that you did in the BGE when you looked at different particles and how they are arranged in the different states of matter. So that, well, there's more than 3 states of matter, but broadly solids. In a solid, you'll see that all the particles are stuck together and they don't take up the shape of the container and they don't fill the volume of the container. So they've got a fixed shape and a fixed volume. Okay. Now, for a liquid, the particles are still all touching, but they're able to spread out to fill the shape of the container. So it takes on the shape, but it doesn't fill the entire volume of the container. In a gas, the molecules spread really far apart. So in a gas, the particles take up both the shape and the volume of the container. Okay. In a solid and a liquid, the particles are always touching, and we know that the reason why something changes from a solid to gas is because the particles vibrate, and then they vibrate so much that either to change from a solid to liquid, they break some bonds, are able to slide over each other, and to break from a liquid to gas, they become much farther apart, okay? So, let's start taking notes then. Everything in this blue box is something that needs to be in your notes, and you need to just pause the video to take notes as needed. An introduction to molar volume then. So when measuring out solids, we usually weigh them to find out their mass. The mass can be converted to moles by knowing the gram formula mass of the substance. So the number of moles is the mass divided by the formula mass. So we're happy with that. Number of moles is mass divided by the gram formula mass. Gases are extremely difficult to weigh. They have low densities and spread out easily. Also, most gases are colourless, so it's very difficult to know if we've captured the gas in the appropriate container. So it is more appropriate to measure the volume of a gas, okay? So volume, which we would measure in litres or in centimetres cubed, or sometimes in millilitres, okay? So the molar volume is the volume which 1 mole of a gas occupies. That's our definition, the volume which 1 mole of a gas occupies. It is measured in litres per mole, okay? So don't get confused between litres per mole and moles per litre. It can be calculated by dividing the volume, which is in litres, by the number of moles. So we can write it like this. This Vm, which means the molar volume, is the volume divided by the number of moles. So because the volume is measured in litres and the number of moles is measured in moles, then we're dividing litres by moles, so it's litres per mole. Okay, so that's the units. Okay, so let's think about the molecules in a gas. So the molecules in a gas are very far apart, as we saw in our particle picture. Most of the volume of a gas is empty space. Less than 0.1% is due to the actual molecules. So if I draw out what this looks like, so here are two boxes. Well, that didn't really work out, did it? Try and make them roughly square, okay? And let's say we've got in this first one, we've got some particles. Okay, 1, 2, 3, 4, 5, 6. Okay, so the particles are spreading really far apart. Now, one of the fundamental aspects of molar volume is that it doesn't really matter about the size of the molecules. That's quite irrelevant, because the most important thing is the space between the molecules, and there's loads of space. So even if we compared it to another gas where the molecules were much larger, they would still be able to fit in the same space, within the same volume, because there's still just mostly space between them, okay? So the molecules in a gas are very far apart. There's plenty of space. Most of the volume of a gas is empty space. Less than 0.1% is due to the actual molecules. So what we can say is, according to Avogadro's hypothesis, equal volumes of all gases at the same temperature and pressure contain equal numbers of particles. So that means if you've got a mole of hydrogen or a mole of helium or a mole of argon or a mole of carbon dioxide or a mole of sulfur dioxide, they would all take up roughly the same volume, because it doesn't really matter the size of the molecule. The thing that's the same really is the space that's between the molecules. So since the total volume that a gas occupies is made up primarily of the empty space between the molecules, the actual size of the particles themselves is nearly negligible. Negligible, remember, means not worth counting towards the total. Just like when we say the mass of an electron in an atom is negligible. We're not saying it's zero. We're saying that it's so close to zero that we're not going to count it when we look at the mass of an atom. So it's the same when we're thinking about molar gas. It's not that the size of the molecules has zero effect, but we're saying that it has almost no effect, such that we can say that equal volumes of all gases will contain equal numbers of particles. Okay. So for example, a litre of gas with small light particles such as hydrogen, which has the formula H2, contains the same number of particles as a litre of heavy gas with large particles such as sulfur hexafluoride. Okay, so 1 mole of hydrogen actually weighs 2 grams, okay? Because remember, it's H2, the relative atomic mass of hydrogen is 1. So a molecule of hydrogen would be H2. And a mole of sulfur hexafluoride weighs 146 grams. Okay, so if we were to weigh these gases, then 1 mole of hydrogen would be much lighter than 1 mole of sulfur hexafluoride, but the gases would occupy the same space. They would have the same volume. Okay? Now we're going to think about the effects of temperature and pressure. And this actually relates to some laws of physics, okay? Charles' law and Boyle's law, which we don't need to know about in detail at all, but I just wanted to show you these diagrams to give you an idea of what is happening and why we need to compare gases at the same temperature and pressure, okay? So temperature affects the volume that a gas takes up, because as we increase the temperature, going from temperature 1 to temperature 2, you can see a lower temperature here and a higher temperature here, then the volume that this gas is taking up increases. So as the temperature increases, the volume increases, okay? remember that temperature is a measure of the average kinetic energy of particles, that the particles are moving about faster and they want to take up more space. When we're looking at pressure, so here's our low pressure and here is our high pressure. When we've got low pressure, we've got a larger volume, and when we've got high pressure, we've got a smaller volume, okay? So as the pressure increases, the volume decreases. Let's summarise that then. So gases are affected by changes in temperature and pressure. Volume is directly proportional to temperature, so as temperature increases, volume increases, and pressure is inversely proportional to volume. So as pressure increases, volume decreases. We just need to know the trend there, and we need to be sure then that when we're comparing gases, so if I'm saying to you that 1 mole of gas occupies the same volume as any other gas, I always need to stipulate that it must be at the same temperature and pressure. So molar volumes of gases can be compared if they are at the same temperature and pressure. Common molar volumes we see would be 22.4 litres per mole. And that is something called standard temperature and pressure, or STP. And that refers to 0 degrees Celsius, and 1 atmosphere of pressure. We also can see often 24 litres per mole. That refers to room temperature, 20 degrees, and the same pressure, 1 atmosphere of pressure. Okay? So often in questions about molar volume, you'll see something like assume molar volume of 24 litres per mole, or assume molar volume of 22.4 litres per mole. And so if a gas is measured under fairly normal conditions, so lowish temperatures and a lowish pressure, then we'll be looking for numbers around about the 22, 23, 24 litres per mole mark, okay? That is what kind of normal molar volume would be like. But we know that in industrial processes, we can really alter the temperature and really alter the pressure, which then would change what the molar volume would be. Okay, we're going to now look at some examples of these. Now I'm going to go through 8 examples, and I would probably suggest that you copy them down with me so that you have a complete kind of set of how to work through these types of questions. Today, all we're concerned about is being able to use the equations that we've learned to work out molar volume or number of moles given the unknowns, okay? So let's work through these together then. First question is, which has the greater volume, 4 grams of hydrogen or 44 grams of carbon dioxide? So we know that if we had 1 mole of each of them, they would occupy the same volume, okay? So this question is actually only looking at our knowledge of this relationship. Number of moles is mass over the gram formula mass. So think about hydrogen then. Well, hydrogen is the diatomic gas with the formula H2, and carbon dioxide has the formula CO2. 1 mole of each of these then. So let's say the number of moles for carbon dioxide, let's actually do hydrogen first. For hydrogen, number of moles is mass divided by gram formula mass, where the mass from the question is 4 grams, and the gram formula mass, if it's H2, so that would be 2 times 1, which is 2. So 4 over 2, that means we've got 2 moles. Okay, so we've got 2 moles of hydrogen. Then let's consider the carbon dioxide. So for the carbon dioxide, the number of moles, again, is the mass over the gram formula mass, where the mass from the question is 44 grams, and the gram formula mass, so CO2, we've got 16 times 2, which is 32, plus 12, which is 44. So 44 grams over 44 is 1 mole. Okay, so we've got 1 mole of the carbon dioxide and we've got 2 moles of the hydrogen. So based on that, the hydrogen would have the greater volume because we have more moles of it. Okay, we have 2 moles of hydrogen, but we only have 1 mole of carbon dioxide. Okay, so next question, this is exactly the same type of question, but just different volume, different masses and different substances. So again, we're just using N equals M over GFM. We've got sulfur dioxide and oxygen. So let's do for sulfur dioxide, number of moles is mass over gram formula mass, which is 6.4 over 64.1. So what you can calculate the gram formula mass by adding up the sulfur, which is 32.1, and 2 oxygens, which are 32. So you get an answer which is 0.09 something, but it's basically 0.1. And then for the oxygen, same calculation, just inserting the different numbers. Again, oxygen is diatomic, so when you look up the relative atomic mass for oxygen, it's 16. We need to multiply that by 2. So we've got 8 grams divided by 32, which is 0.25 moles. Just write moles over here as well. Okay, so we've got how many moles for each, and then because this is the bigger number, then this is what would have the greater volume, okay? 0.25 moles of a gas is going to take up more space than 0.1 mole of a gas. Okay, question 3. Calculate the volume of 2.8 grams of ethene with the formula C2H4. Take the molar volume to be 23.6 litres per mole. So for this question, we need to have both of our equations ready. So number of moles is mass divided by gram formula mass. And also the molar volume, the volume, that's what we're going to have to calculate. The volume is equal to the molar volume multiplied by the number of moles. So from the question, I can see that I've got a mass and I've got the name of a substance, which I can then work out the gram formula mass. So let's insert those numbers then. If we've got C2H4, then that's going to be 4 plus 2 12s, which is 24, which is 28. So it's going to be 2.8 grams divided by 28, which is 0.1 moles. And then I have the molar volume from the question here, 23.6, and I have the number of moles, 0.1, so I can insert those here into this equation. So that would be 23.6 times 0.1, which would be 2.36 litres. And that would be the final answer for this question. Okay, so that's the volume that mass of ethene would take up, given that 1 mole would take up 23.6 litres. Okay, next question. Calculate the volume occupied by 0.3 grams of ethane, assuming the molar volume of 24 litres per mole. Okay, so again, we've got these two equations. I'll write them out as triangles this time so we can work out what we need to know. So volume is the molar volume multiplied by the number of moles, and number of moles is the mass divided by the gram formula mass. So again, from the question, I have a mass and I know which substance. It's ethane. So ethane, C2H6. So 6 plus 24 is 30. So 1 mole of ethane would weigh 30 grams. How many moles if I've got 0.3? Okay, so number of moles is 0.3 grams from the question up here, divided by the gram formula mass, which is 30. So 0.3 divided by 30 is 0.01 moles. Okay, and then if I've got a number of moles that I've calculated, so that's going to go up here, and then I've got a molar volume, which is going to go here, then I can work out the volume by multiplying those numbers together. So volume is the molar volume multiplied by the number of moles, so that's 24 litres per mole, multiplied by 0.01, which is 0.24 litres. And that is my final answer for this question. One thing to bear in mind is that sometimes the volume is given in centimetres cubed. So if we were asked to convert, or it might be asked for in centimetres cubed, so to convert that would be 240 centimetres cubed, or 240 millilitres. Okay, next question. The volume of 0.22 grams of propane, and we've got the formula there, is 118 centimetres cubed. Calculate the volume of 2 moles of propene Oh, that should be an A. Let's just change that. Propane at this temperature and pressure. Okay, so we need to start off with, well, what have we got first? We've got a volume and we've got a number of, no, we need to work out the number of moles first, don't we? Yeah, so we've got a mass and then we know the formula, so we can work out number of moles using N equals M over GFM. So mass is 0.22 and GFM for propane, so C3H8 is 44. So 8 plus 36, is 44. So 0.22 divided by 44 is 0.005 moles, okay? So then we can work out the molar volume by saying, well, that's the volume divided by the number of moles. Now, the volume in this question is given in centimetres cubed, so we need to convert that to litres. So that would be 0.118 litres, and divide that by the number of moles, which is here. So that would be 0.005 moles. And we get a molar volume of 23.6 litres per mole. Now, that's just part of the answer. So we've got something, but it's not everything that we need to answer the question, because the final part of the question says, calculate the volume of 2 moles of propane at this temperature and pressure. So there's a couple, well, you could think, well, I know that 1 mole takes up 23.6 litres per mole, therefore 2 moles would take up 47.2 litres per mole. So that's just multiplying it by 2. But to bring it back to the equation, volume is molar volume multiplied by the number of moles. So the volume would be 23.6 litres per mole multiplied by 2, which is the number of moles you've got. So that is 47.2 litres. Okay, the answer is in litres because we've been asked for a volume. Okay, and that is that answer there. Okay, next one. This question is asking us about fluorine. So calculate the volume occupied by, we've got a mass of fluorine, assuming the molar volume of 24 litres per mole. So fluorine is the diatomic molecule F2. So 1 mole is 38 grams. And to work out how many moles I've got, I need to do N equals M over GFM. So 0.76 divided by 38, which is 0.02 moles. Okay, and then I'm going to say, well, the volume is equal to the molar volume multiplied by the number of moles. So that is going to be 24 from the question multiplied by this number here, 0.02 moles. And that is going to be 0.48 litres or 480 centimetres cubed. And that's my final answer for this question. Okay, something to bear in mind for this question is if you're not given the formula, it's easy to forget which elements are diatomic and therefore miscalculate how many moles you have of that. So just be aware of that too. Okay. Here's a question that is actually simpler than it looks. Okay, so it says calculate the molar volume of 0.226 moles of butane in a 5 litre flask. So if we want to carry out a molar volume calculation, so molar volume is volume divided by number of moles, we actually already have that information from the question without having to work out number of moles or deal with the gram formula mass of butane, because we already have a volume, which is 5, and a number of moles, which is 0.226. So let's pop that in then. So 5 on the top line, 5 divided by 0.226, and that is 22.1 litres per mole. Okay, so actually only one line of working required there to get to the final answer. And this butane, I mean, it could have said anything, could have been any gas that was in there, and the answer would have been the same. One final example for us then, just to make sure we're really happy with this. So we've got a question that's asking us to calculate the volume of 0.14 grams of nitrogen, assuming molar volume is 23 litres per mole. So we'll just do number of moles is mass divided by the gram formula mass for the nitrogen. So that's 0.14 divided by, well, nitrogen again is diatomic. So one nitrogen's relative atomic mass is 14. So 2 14s are 28. So that would be 28. 0.14 divided by 28 is 0.005 moles. And then I put that into the other equation where volume, which I'm asked to calculate, is molar volume multiplied by the number of moles. So 23 multiplied by 0.005, and that is 0.115 litres. Can't see the point there. Or 115 centimetres cubed. So that's some examples of how to calculate molar volume and how to manipulate masses, formula masses, and number of moles to calculate either molar volume or volume in a question.